Hello everyone. Today I'm going to be solving A 2 to 3 moves, which is the first problem of CodeForces round 133. Yeah, let's get into it. So you're standing at a point 0 on a coordinate line, and we're trying to reach N. And you can either move by 2 or 3 to the left or to the right, and we need to solve for the minimum number of minutes to get from point 0 to point N. And I should say that each move requires a minute, so we gotta basically try and limit the number of moves we got. So just looking at the input, we get the test cases, number of test cases, and then we get each test case, which is a number n. So it looks like based on these constraints, we gotta solve it in like O of 1 time, or not O of 1, but like some constant time. And I'm looking at, and we need to output the minimum number of minutes for each one. All right, cool. So let's think about this one real quick. So I'm gonna delete this, get blank canvas right here. So the way I like to look at this is first let's start from the basics. So like what's the answer for something like n equals 1? And that one would be like, I mean, it has it here, but it would be x plus 3, and then we could subtract 2 to get back to 1. And I think that's the best way because there's no plus 1 move. That would get us 1 move. The best we could do is like a plus 3 and then minus 2. So that's why we get something like this, which is 2 moves right here. And then for, of course, n equals 2, we could just plus 2, and then we'll have 1 move there. So 0 plus 2 would be a 1 move. And then for something like n equals 3, we would have 1 move because this would just be a plus 3 right here. So now, how do we now have like the simplest cases, but like how could we get for something like n equals 4, or like keep going to like any arbitrary n that's greater than our base cases? So the way we could do this is, well, if I'm looking at this right here, we could build off our previous cases. So we could start from n equals 2. We know the shortest way to get to 2 is 1 move, and we could just do a plus 2 here, and this would therefore be 1 move. 2 plus 2 takes 1 move to get to this 2, n equals 2, and we add 1 more move, so we'll have 2 moves here. And then here we could have for n equals 5, we could have 0 plus, we could build off of either the 2 or the 3. So I'm gonna build off the 3 this time, and we'll have 0 plus 3 plus 2, and that'll give us 3 moves. Or actually, my bad, 2 moves, what am I saying? And then for n equals 6, it would just be 0 plus 3 plus 3, which is also 2 moves. So I know this is the answer, but like, how do we prove that there's no better way than using 2 moves to get to something like n equals 4? So the reason why I know that's the fewest amount of moves to get to 4 is because the max distance we can cover in the positive direction is plus 3. And we know for 4, the only way we get to 4 is through at least 2 moves, because we can only cover plus 3, and then we would need another either plus 3 or something to cover that distance again. So that means the minimum has to be at least 2 moves in order to get to that 4, because we can only cover a max of 3, and that's the same for 5. We would need at least plus 3 and a plus 3 to get there, because that would give us a plus 6, which is greater than 5. So therefore I can generalize this, and for any n we could get, okay, we need at least n divided by 3 moves, and not just n divided by 3, but the ceiling of this right here, because we would need to get to n. So for something like n equals 7, for example, we could do a plus 3 and a plus 3. That would be 7 divided by 3 is 2. It enters division for programming, right? But we would need 1 more move than that. So that's why it's the ceiling. So we need an extra number, a plus 1 added to the n divided by 3. And that would give us a plus 9, which is at least 7. And therefore, we can just see, if I keep building off here, n equals 7, 0 plus 3 plus 0 plus 3. This one I could build off of from the 4, so 0 plus 2 plus 2 plus 3, which equals 3 moves, n equals 8. This one's 0 plus 0 plus 3 plus 2 plus 3, which is equal to 3 moves, and so forth. And you can see that for each one, we're reaching, the answer is the ceiling of n divided by 3. Because here, 7 divided by 3 is equal to 2. And the ceiling of this is actually 3. So using this recurrence relation, so kind of just taking the current n and taking either the min of n minus 3 or n minus 2, the steps to get to these at least. So if, like, let's say I have a function f of n, and this is the number of moves to reach n. The current n, so like basically our recurrence relation would be f of n is equal to the minimum of f of n minus 3 and f of n minus 2, which it doesn't matter because they're going to be the same thing, but it's just to like show the recurrence relation. Min of these, so the number of steps to get to here, number of steps to get to between these two, and we add 1 to that because we're going to add one more move to get to where we're at, because we're going to do a plus 3 or plus 2. And therefore, based on this, we can always see that, and with our base cases being f of 1 is equal to 2, we don't even need that base case. Our real base case is f of 2 is equal to 1, f is equal to 1, f of 4 is equal to 2, because this is equal to the minimum of f of 1, f of 2, which is a fact. I'm going to even write this out. Minus 3, f of 4 minus 2, plus 1, which comes out to be f of 1, f of 2, plus 1, which is equal to minimum of 1, 2, 1, plus 1, which is equal to 2. So you can see how the recurrence relation, all that nonsense, we don't need all this stuff, but just to like show out the math, since we gotta seem smart, right? F of 5 is equal to 2. And we can see that all these n's, all these f of n's end up being the ceiling anyway of n divided by 3. So based on this, we know that it takes at least this amount of moves, and our recurrence relation shows that it ends up being the ceiling of n divided by 3 anyway. So like for 4, the ceiling of 4 divided by 3 is 2 anyway. Same for 5, it's 2. 6 divided by 3 ceiling is 2. 7 divided by 3 is 3 moves. So therefore, we know it's at least this, and it ends up being this due to a recurrence relation. Well, the answer must be then, if n is equal to 1, it's 2, but for any n greater than 1, it'll be ceiling of n divided by 3. And that's the answer. So like, what we could do now is kind of do the coding. So we get as input a t, and then we also get for each test case an n. So if n is equal to 1, we're going to just output a 2, and we'll continue. And if not, then we'll have a res, that's this division, and then if n is not divisible by 3, then we'll increment res by 1, because that's like our ceiling right there, you know what I'm saying? So then we print that, and then we'll see if that works. So usually it's good practice to test out the first batch of test cases, but I have a feeling this is gonna work, so we'll see what happens. And it looks like it accepts. So that's how you do it. That's 2 3 moves in a nutshell. Not a super complex problem, but I think it's a very, very interesting one to understand, and kind of like helps you sort of formulate a cool solution by breaking it down to simple steps, starting from the base case and then building up that recurrence relation, and then solving for it that way, and sort of like proving, there's sort of like kind of a proof involved to make sure that's like the optimal answer for each one.